In this series of videos, we start to look at alternative coordinate systems, our first one being polar coordinates. Recall that in polar coordinates, x is equal to r times the cosine of theta, and y is equal to r times the sine of theta, where r is the distance from the origin to a point in the xy plane, and theta is the angle made with the positive x-axis. Also, we have that x squared plus y squared is equal to r squared, and that the tangent of theta is given by y over x. In the rectangular coordinate system, the fundamental unit for area is the rectangle. That's usually given as delta y, delta x, or delta x, delta y. In the polar coordinate system, the fundamental unit for area is a polar rectangle. Let's look at a diagram. Here we're looking at a portion of a polar grid, and the highlighted gray area is a polar rectangle. It's defined by constant theta values, theta 1 and theta 2, and constant r values, r1 and r2. Let's single out one polar rectangle inside of this polar rectangle. Let's call this the ith subinterval. So we're looking at r sub I minus 1 and r sub I as the bounds, the r bounds for this rectangle, and then theta sub I minus 1 and theta sub I as the theta bounds for this little rectangle. Now let's focus just on this green one, and let's blow it up a bit so we can see it better. Let's say the angle theta here, which is given by theta sub I minus theta sub I minus 1, we're going to call that delta theta. And then we're going to say we have a width here of delta r. If we make delta theta and delta r small enough, then we effectively really have an actual rectangle. We just need to figure out the dimensions of the rectangle. Well, we have one of them, delta r. For the other one, we need an arc length. Remember that in general, an arc length, I don't mean the integral arc length formula, but arc length that you would have seen in trigonometry is s is equal to r theta. Well, in this case, we're going to say that r is r sub I, theta is delta theta. So here we have that s is equal to r sub I times delta theta. That makes the area of the ith subrectangle equal to r sub I delta theta, right? That's our, let's call it width, times delta r, which we're going to call our length. With this in mind, we have that the double integral over region r of f of x, y, dA becomes the integral from alpha to beta of the integral from a to b of f of r cosine theta, r sine theta, right? We are now converting into polar coordinates. And this dA is represented by this r times delta r delta theta. In the language of differentials for integrals, this is going to be r dr d theta. That is to say that dx dy or dy dx is represented as r dr d theta. So to convert an integral from rectangular to polar coordinates, we replace x by r cosine theta, y by r sine theta, or, folks, sometimes it's just more convenient to replace x squared plus y squared by r squared. And then, instead of dy dx or dx dy, we write r dr d theta. Here's the most common mistake. What do you think it is? Can you guess? People forget the r. Now, the limits on r are going to be a to b in this, for this picture here, and then the limits on theta are going to be alpha to beta. Right now, just take a moment, wherever you're sitting, just out loud, r dr d theta, r dr d theta. Just repeat it to yourself a few times. If there are people around you, I promise you, they're going to leave you alone. Here we're going to say that, as I said, r is between the constants a and b, and theta is between the constant angles alpha and beta. However, if r1 is given by h1, a function of theta, and r2 is given by h2 of theta, assuming that h2 is greater than or equal to h1, then we have the integral from alpha to beta of the integral from h1 of theta to h2 of theta of f of r cosine theta, r sine theta, and then what comes next, folks? That's right, r d theta. Now what we did a moment ago with this using the arc length and the outer r sub I might have seemed a little bit squirrely. I mean, it's legit. I tell you, it's legit. But for those of you who felt a little squirrely about that, let's look at another justification. And this is another justification for a sub I being r delta theta. We have here again our polar rectangle where r goes from r sub I minus 1 to r sub I, and theta goes from theta sub I minus 1 to theta sub I. And we can express a sub I as being the difference of the outer sector minus the inner sector. I'll call that a sub 2 minus a sub 1. And remember that the area of a sector is equal to 1/2 r squared theta. So a sub I is equal to, well, a2 is going to be the area of the larger sector. And so 1/2 r sub I squared times delta theta, again, assuming the angle in here is delta theta, minus 1/2 r sub I minus 1 squared delta theta. Well, we can factor out the 1/2 and the delta theta, and what we're left with is r sub I squared minus r sub I minus 1 squared. And inside the parentheses, we have a difference of squares. So a sub I is equal to 1/2 of r sub I plus r sub I minus 1 times r sub I minus r sub I minus 1 times delta theta. Well, r sub I minus r sub I minus 1 is delta r. And then we're going to replace half of r sub I plus r sub I minus 1 by r sub I star, the average of the two r values. And it doesn't matter really if we use the inner r value or the outer r value or the average of the two r values, because we're going to let delta r go to 0 if we were setting this up as a Riemann sum, which I'm not going to write. But this concludes as a sub I is equal to r sub I star times delta r delta theta